Okay, I did a video on the universal set, and I'd like to talk a little bit more about it from a more rigorous standpoint. And that would be how to maybe address the paradox of the universal set in a way where it wouldn't be such a paradox. I'm not arguing that there is a universal set. In fact, even theistic philosopher Alvin Plantinga, you would think would believe in the universal set, actually doesn't seem to believe in it. Although he believes in the possibility of omniscience, he doesn't believe in the idea of the universal set, and even seem to downplay Cantor's diagonalization and argument, and which I'll review in a minute, by the way, for those of you not familiar with it. What we're discussing is the issue: is there a universal set? And the question is, if there is a universal set, then what of the power set of that set? And according to Cantorian arguments, that the power set of a universal set would be greater than the universal set, uncountably greater, but that would contradict the idea of the universal set. There is a paradox, QED, we cannot construct a universal set. There, that's the argument in a vastly oversimplified nutshell. I'd like to see if maybe we can find a way around it. And this is speculation, it's not an argument. Let's review the diagonalization argument as Cantor provided it. Now, Cantor proved that you could pair integers with rational numbers, i.e. with fractions. Okay, he proved a lot about what we could pair. You could pair all the rational numbers between 0 and 1 with all the rational numbers between 0 and 100, according to Cantor. I mean, that's how far he went with pairing and one-to-one correspondences. But when it came to irrational numbers, he noticed something. Let's say we have all irrational numbers between 0 and 1, okay, which, by the way, compare to all the irrational numbers on the number line, okay? So it's a fit comparison. 0.A1, A2, A3, A4, 0.B1, B2, B3, B4, 0.C1, C2, C3, C4, 0.D1, D2, D3, D4, and then you keep going, E, and then you just go on down to infinity, and you're assuming a priori that you have something countable. But note, okay, so that's the a priori assumption, but note what he did. And for those of you who want to read more about this, you can go to YouTube or the internet. There's all sorts of sites on it. And for those of you who want to know how he paired rational numbers with integers, you should explore that too, because it's interesting. I don't have time to do that here, because I want to get to the point. But just for a brief review, he took the first digit of the first number, the second digit of the second number, the third digit of the third number, the fourth digit of the fourth number to infinity, and then he added 1 to each digit, and I guess maybe turning 9 to 0, okay, you know, which would be equivalent to adding 1, but no carryover of the 1, okay. So A1, and you got A1 plus 1, B2 plus 1, C3 plus 1, D4 plus 1, which does not fit into any of these numbers here. It would have to be different than all of these numbers, because the first number, the first digit of the first number is different, the second digit of the second number is different, the third digit of the third number, and so forth. That is a unique number. If I were to input that in back at the top, okay, layer it up there and do it all over again, I would again get a different number, and again get a different number, and again get a different number. So voila, the reals are uncountably greater than the rationals. Okay, the rationals and the irrationals together are uncountably greater than the rationals. And from there we have the whole idea of the power sets and levels of infinity. Is there an ultimate level of infinity? Well, Cantor and most set theorists would say that the problem is that you would then have the power set of that level of infinity. You know, how would you prevent that from occurring? May I pose something through example as maybe a way of looking at it? It's not an ironclad argument, but it's a way of looking at it. Let's suppose I had the rationals, not the irrationals, but the rationals between 0 and 1 instead. And let's suppose two cases. One case where I would have them all terminating, or as another possibility in that case, I have terminating, let's say I have all terminating. Okay, and it's just all terminating, that you have a finite number of a string of digits, and then I have just zeros going on forever, okay, for all of them. And I were to do the diagonalization argument, yeah, I'd have a string of digits here, but I would have a finite And I would have a rational number, but I would have one that would have a finite number of digits and then ones going on forever. And so I would have a situation whereby I would have a number here through diagonalization, but it wouldn't contradict our assumption of the countability of rational numbers that terminate between 0 and 1. Now let's say I had a second case where I had either all repeating or repeats and terminations mixed together. Voila, I have a number here through diagonalization, but I know, let's say I didn't know that you could pair the integers and the rationals. Okay, let's say I didn't know anything about that, and so I thought, well, let's see, are rationals countable or not? I would go through the process and I would have a number here, but I wouldn't know in that instance whether this number was rational or irrational, and so I wouldn't have a paradox or anything like that. I wouldn't be able to, I could easily assume that this would have to be an irrational number and it would fit. Now, I do happen to know that you could pair integers and rational numbers, so I know actually that this has to be irrational based on that. What's my point? In both instances, I've gone through a diagonalization, but it hasn't been philosophically meaningful. Is it possible? No, I don't think any mathematician would disagree with what I just said. They might tweak on how I said it, but they wouldn't disagree with the ultimate point of what I just said. The question is the universal set potentially definable as the set such that the power set of that set is not philosophically meaningful? In other words, the universal set is the universal set of all valid truths that are philosophically meaningful. Could you construct such a set such that the power set of that set is meaningless? They are either not, the power set of that set would either correspond to something not true or just something that would be meaningless statements. That's the question that I pose. And yeah, I'm not saying that that is possible, but I'm bringing up the possibility that you could have a set such that any diagonalization argument becomes meaningless. In fact, we just did with the rational numbers. Could it be that, that's the lowest level of infinity? Could that also apply to the highest level of infinity? And yeah, well, by all means, I want to thank those of you who've been loyal watchers of this channel. A lot of you have agreed, a lot of you have disagreed, but it's been fun. Thank you.